Hiya, for chapter 15, we're going to start looking at how we can use our sample data to actually make inferences about the population. How can we use actually the regression line from our sample data to make inferences about the population? To do that, there's a couple things we need to do first. So here I have an example for you that shows you a basic regression line. This is just for a set of data similar to the Corvette data we were working with. It's the age of a car and the price. It's not the same data values, but it's similar. And you can see the y hat and the small case b sub o and b sub 1, y-intercept and slope relate to the actual sample regression line. But somewhere, which is unknown, unless of course we had every possible data value that exists, is a population regression line. And we don't know what that is. It exists somewhere. Hopefully it will be very close to the regression line we got from our sample. But just so you can see the difference in how we write the population regression line, we're now talking about a capital B sub O for the y-intercept and a capital B sub 1 for the slope and just y. Again, this is unknown. But to use that sample regression line to make predictions or inferences about our population data in general, there's a couple assumptions we have to make, and we've gone through this every time we've worked with hypothesis testing in this course. So the assumptions we would need to make here are listed here. So for the population regression line, there are constants, capital B sub O and B sub 1, such that for each value x of the predictor variable, in this case age, the conditional mean of the response variable is B sub O and B sub 1. So that means if we took the mean, of each individual x, so if we took the responses for year 1 or responses for year 2, and we took the mean of those responses, we would get this particular regression line. This is kind of seen better down here. In other words, say for a 7-year car, there's going to be a lot of different outcomes for a 7-year car. But the hope is all of those outcomes are kind of closely related to the outcome we would get using our regression equation. And so we'll skip down to number 3 for a second. For each value of the predictor variable, the conditional distribution of the response variable is normally distributed. So that means for every car of age 7, we have a normal distribution of responses. For every car of age 5, we have a normal distribution of responses. We also have equal standard deviations. The conditional standard deviations of the response variable are the same for all values of the predictor variable. So that's kind of saying that the standard deviations, these normal curves, pretty much all have the standard deviation. They all look very similar in shape. And we have independent observations, of course. The observation and response variable are independent of one another. So these are the main assumptions that we need to have checked before we can go ahead and feel confident that our equation is good for making predictions. To do this, or to check these responses, we're going to do something called a residual plot. So before we do a residual plot, I want to introduce, one new variable called the standard error of the estimate. So the standard error of the estimate, if you recall, SSE was actually the summation of each individual y value, the difference between that and the y value you would get using the regression equation squared. Okay? So the standard error of the estimate is basically the standard error of all of our, what we call our residual values, or our E values. A residual value, as you can see down on this graph, is that difference that is occurring between our raw data point and the predicted value we would get the response variable we would get if we used our regression equation. So it's the difference in the observed value and the predicted value of the response variable. That's our E. They are residuals. You can think of them as errors. If we took all of the errors, so we have points that are going to fall near and around this regression line. If we took all of these errors and found their standard deviation, essentially we would get this, the standard error of the estimates. We're also going to use those residual values to make a residual plot. And we're going to go over what a residual plot is and what one looks like. When we make a residual plot, what we're looking for in our residuals. So we zero them out here, and I'll go over in detail how to make one with an example in a second. And our residual plot ends up being these data values that fall somewhere around our zero line. Now, I'm going to give you an example of a couple different residual plots for a second. And a third one. Here's our zero line. So when we make our residual plot, to say that our assumptions have been met, what we're kind of looking for is this symmetrical horizontal band that is occurring around our zero value. Notice in the first one I did, we kind of have that symmetrical horizontal band. But notice in number 2, we do not. Okay? There is no symmetrical horizontal band. And in number 3, there is not either. It kind of starts off closely related and then becomes much bigger as the x values increase. We would say that our assumptions have been met with number 1, but not with number 2 or 3. So what you're looking for is when you do a residual plot, to be confident that your assumptions have been met, you're kind of looking for the first graph. So what I want to do is go ahead and use the data we were working on in our other lessons, which was the Arizona Stat Calculus class. The predictor variable is the total study time over 2 weeks. That's your X value. And the response variable is the grade on the test you received over 2 weeks. We already found in a previous lesson the regression equation. So in order to get our residual or E values, what we need to do first is calculate using our regression equation. We did this in a previous lesson where I gave you 2 regression equations. You had to find the one of best fit. This is not either of those equations. This is the actual regression equation we calculated in one of our other lessons. So let's go ahead, and the first thing I want you to do is plug in all your values for X into this regression equation and see what we get for Y. That would be your Y hat values. So double check. This is what I got when I plugged in each X value into our regression equation. So when I plugged in a 10, I got 86.407. When I plugged in 15, I got 82.177. And if I made any mistake in there, I'm sorry. You can send me an email and I'll put an email out that it's wrong. From there, we are going to find our E values. Now you are not going to find this particular formula on your formula sheet, I don't believe. So you have to know that your residual values are the raw data minus the value you get when you plug it into the regression equation. So for E, the first one, E sub 1, is going to be the raw data 92 minus 86.407. So 92 minus 86.407. And we get 5.593. So what I want you to do now is go through and find all of the E values, the residual values for this particular set of data. So this is what I got when I plugged in, when I found all the residual values, and I took the Y values minus the Y hat values. I got this list of residual values. So to make our residual plot, what we're going to do is the x-axis is going to be our x values. So our x values need to go, looks to be 8 to 22. So 1, 2, 3, 5, 6, 7. So it's 8, 10, 12. I'll just go by 2s. Just come up with a scale that kind of makes sense. And start plugging in and put your x values across the bottom. And then on the y-axis, you're going to plot your residual values. Now notice your residual values, some are positive and some are negative. So we're going to do is zero them out here in the middle. Figure out what the furthest one away is. It looks like the furthest one from 0 is 5.59. So we need to go 6 in either direction to keep it consistent. So we'll go -2, -4, -6, and then 2, 4, 6. Whatever scale, you can use whatever scale you want. Just keep it consistent. Whatever scale you use above the 0, you use below the 0. Okay, just because I went by 2s on the x-axis doesn't mean I need to go by 2s on the y, but you do need that consistency above and below. And we're going to plot. So at 8 hours of study time, our residual is -3.9. So that was close to 4, so that one's right there. At 10 hours, it's going to be 5. It's going to be up there. And sometimes you're going to have multiple. We don't have multiple in this particular set of data, but you could have a couple points on one x value, and that's perfectly fine. For 12, it looks like we have -9, so that's about right there. For the, what else do we got? Let me see. Let me do them in order because I was messing up a little bit. So the 10, we had the 5. 15, which is in the middle here. 15, I'm going to go to -1, which is about up there. I'm looking at this, sorry, I'm looking at it on an angle. So let's go. 15 is going to be up here. We have 12. 20 is at -3. 8 we did. 16 is at -1. 14 is at +1. And 22 is at a 3. So this is a small set of data. So because it's so small, you're just looking for some sort of horizontal symmetry. It's hard to say with this small set of data whether we have it or not, but I would say we kind of have some horizontal symmetry here and here. There is a nice horizontal band we can draw, and the numbers are pretty evenly dispersed within that band. So that's essentially how you do a residual plot. And the next video, we'll go back to hypothesis testing when we look at inferences.